You're looking at a US penny sprinkled with grains of salt. And here's the part that breaks your intuition. Scientists have now built fully autonomous robots that are smaller than those salt grains. Not tethered lab demos, not remotely controlled toys, but real machines that can sense their environment, make decisions, move on their own, and keep doing that for months without wires, remote control, or magnetic steering. And each one costs about a penny to make. Each robot measures exactly 200 by 300 by 50 micrometers, roughly the size of a paramecium, a single-celled organism. Two of them side by side are about the width of a human hair. You can barely see them without magnification, yet inside that microscopic footprint is a complete computer with a processor, memory, sensors, and a propulsion system with no moving parts. These robots don't wait for instructions. They operate autonomously. This breakthrough came from a 5-year collaboration between the University of Pennsylvania and the University of Michigan. Mark Miskin from Penn Engineering led the robotics work, while David Blau's team at Michigan built the computer. That matters because Blau's group already held the record for the world's smallest computer. The two teams met at a DARPA presentation, realized they were solving opposite halves of the same problem, and decided to combine forces. Researchers have been trying to build autonomous robots at the sub-millimeter scale for about 40 years. Every attempt ran into the same wall. You could get motion, but only with external magnetic fields. You could get sensing, but no independent movement. Or you could hard-code behavior during manufacturing, but the robot couldn't adapt. If a human had to guide it, it wasn't really a robot. The reason comes down to physics. At the microscale, moving through water is like moving through tar. Drag and viscosity dominate everything. Mechanical joints and wheels that work fine on larger robots fail completely when you shrink them down. Biology solved this billions of years ago, and that's the trick Penn borrowed. Instead of moving parts, these robots generate an electric field that pushes ions through the surrounding liquid. Those ions drag water molecules with them, creating a tiny current the robot rides. They're powered by LED light, operate in a hydrogen peroxide solution, and move at about 1 body length per second. Because nothing is mechanically moving, they're extremely durable and can swim continuously for months, even coordinating in groups like a microscopic school of fish. The brain is the real breakthrough. The solar panels on each robot produce just 75 nanowatts of power, over 100,000 times less than a smartwatch. To make a computer work on that budget, Blau's team reinvented circuit design, cutting power consumption by more than 1,000 times. About 75% of the robot's surface is solar panel, and the processor alone uses nearly 90% of the total power. The robots have temperature sensors accurate to within 1/3 of a degree Celsius and communicate their data using tiny oscillating movements that researchers decode through microscope video, essentially a robotic waggle dance. Right now, they operate in hydrogen peroxide, not blood, but the implications are big. Near-term uses include monitoring individual cells and assembling microscopic devices. Longer-term, researchers see paths toward targeted drug delivery, stroke treatment, and cellular-level health monitoring. Mark Miskin told the Washington Post that real medical applications wouldn't surprise him within about 10 years, around 2036. These robots are manufactured using standard semiconductor processes with about 100 fitting on a single chip and a cost of roughly 1 penny each. Companies like Bionaut Labs have already raised $43 million and are entering phase 1 clinical trials with micro-robots of their own. We've spent decades shrinking computers, and now we're shrinking robots, and that shift is just getting started.